Okay, the second part of the lecture is give you a brief introduction to the HLS. Okay, HLS means high-level synthesis. So what it does is convert the high-level language C, C++ into an RTL circuit. Okay, so basically generate the Velo codes or VHDL codes. It does not generate the netlist. Okay, and the for the Velo code, then you use the target toolchain like Xilinx that doing all the synthesis and implementation tools. Okay. So how do you use the directive and pragma to control or direct the compiler optimization process? Okay. So that means you can use the pragma to target to different design targets. Okay, for example, if you want to have a high performance, then you can use pragma specify more parallelism. Okay. And so the synthesis tool will try to optimize for power, performance, area, and timing. Yeah, and this is a typical flow for the high-level synthesis. And first, you have a high-level code. It could be C, C++, or OpenCL. And for Xilinx, for Intel Altera FPGA, it supports OpenCL. And Xilinx used to support OpenCL, but like 2-3 years ago, it dropped the support of OpenCL. So with a given high-level language, first you do the syntactic analysis, okay, and then you transfer into an intermediate representation. Okay, so for all different language, you have a different front end for syntactic analysis, and they all generate the same intermediate representation, and from there you do the optimization. At this stage, the optimization basically apply the standard CPU compiler techniques. And in here, I list they are actually for modern compiler has all kind of optimization. And in here, I only list a few of them. Okay. So after that, then you do the high-level sensor specific optimization. In here, particular, I talk about the schedule and resource allocation, and then binding to the final target hardware architecture or hardware components. So that's actually this part is kind of a data path compiler. However, in today's HLS compiler, it's still a very active field. People try to apply all different kind of pipeline optimization method to optimize it. Especially in academic, people try to capture the senior designer design techniques and incorporate into the HLS compiler. So in the future, actually, it's very close that the HLS compiler can compile a design that's more or less equal to a senior designer. But it still continue evolving. Yeah. And in today's markets, the HLS compiler mostly from the FPGA vendor, in particular the Xilinx VTIS HLS, Intel HLS compiler. And those are the for FPGA. For IC design, people use Siemens Mental Catapult or Cadence 2. And as far as I know, that the Xilinx VTIS HLS compiler probably is the most is better among those HLS compilers. And many focus on backend part, so that's the part we are talking about. And then I will give a very brief explanation about the scheduling, resource allocation, and the binding process. Okay. Okay, these are the topics we're going to talk about in these lectures. Okay, first, not all the C and C++ constructs supported by the HLS compilers. Yeah, and in particularly for us doing more of the hardware design. I'm not talking about that you are doing the pure application, like for UI type of application. We are talking about doing the code that needs much computation powers. Yeah, for this type of programming, the following construct that they are not supported by current HLS compiler. Okay, so there is one guided principle is since we are compiling the hardware design, so all the resources must be statically allocated at the compiler stage. Okay, and for C++, that's this language support a lot of syntax for runtime data structure type of instantiation, and that cannot be possibly supported by the HLS because all the hardware resource has to be statically allocated. Yeah. Okay. So, for example, I think it's quite obvious that system code could not be supported in your. It's not synthesizable. Okay. However, we really like to maintain the same copy of a source code for both C simulation and C RT code simulation. Okay, we like to have a same piece of code. So the common practice is using the Markov define. Okay, so for in the HLS compiler, it has a built-in Markov which is underscore synthesis. Okay, so you can use this Markov to distinguish the part of a code that will be used in the C simulation or not in the HLS. So, for example, for C simulation, you really want to use all kind of C syntax or debugging syntax that's for you easy to do the C application. So you may use a printf and open file and those things. Okay, then you use this Markov synthesis to disable it when you are doing the synthesis HLS compilation. Yeah, I'm talking about this part of a code actually in the HLS kernel function. Okay, if it's a host function, of course you can use all kinds of C language because it's not subject to HLS compilation. Yeah. Another restriction is in HLS you cannot use dynamic memory usage. Okay. So if you know the programming language, that sometimes you do need to have a large memory allocations because the data set is big. Okay, so you use mallocate. For mallocate, it actually is using the swap address. So it could be very large, could be huge size. There's no problem. And for certain C application verification, you do need big data set to verify your functions. Okay, you don't want to be limited to, for example, the way you allocate static memory size, and this memory will be allocated in the stack space. And the stack space is quite limited. That's allocate per process. Yeah, And that will limit how much data size you can run the verifications. Yeah. But in HLS, you do need static memory allocation. Allocate the static memory size. Okay. So in this case, you have to standard or common practice. You define your own macro. Let's say the node synthesis, this macro. So when you are run the C simulation, then you define the you don't define the synthesis. Okay, you define the node synthesis, then you run the C simulation. Okay, when you run the HLS, then you define this node synthesis. Then you will use the static memory allocation. Yeah, and this is the way you convert from the memory allocation to static memory array allocation. Yeah. Okay, so you are not allowed to use a dynamic memory allocation for the HLS code. Yeah. Another restriction is the pointer limitation. Okay. And you know, pointer in C could point to any object. Okay, and different object has a different resource allocations. So in general, that HLS does not allow general pointer casting, but it do support casting between the native C, C++ data type. Okay, and then for a pointer array, if you have a array of a pointer, okay, the pointer either can point to a scalar or point to another array with scalar. But you could not point to array of pointers. Okay, the two-level interaction that the compiler could not handle. So this, you cannot do that. Okay, and definitely the function pointer could not support. Yeah. So that's a pointer limitation. Okay, another is a recursive function. Some programming style, or algorithm. Okay, a lot of algorithm, like a branch and bound algorithm, people use recursive functions. Okay, and recursive function in general is not supported by HLS, simply because for recursive function, its calling depth is really data dependent. Okay, and so it's not determined at the compiler time. Yeah. However, for Taylor recursion, actually it's a loop. Okay, it's a loop in disguise. For example, in this recursive function, this is a typical Taylor recursion. You can manually translate this Taylor recursion code into this one, becomes a loop. Okay, so you either manual convert, or you can have the tool handle for you. Okay, and for HLS, it only support recursion, only support tail recursion in C++, and C they don't. HLS does not support. You have to use C++ because you're going to use C++ the termination class. Okay, so at the final recursion, that's a termination. Okay, that define that's the end. Yeah. So with that information, the HLS compiler can emulate the human menu change to a loop style design internally. Yeah. Okay, so that's a recursion. Okay, so actually that's the typical limitation in C++ syntax that could not be supported by the HLS compilation. Okay, next I'm talking about the C to HLS process. Yeah. So this on the right hand side, that's a typical the C code. Yeah. And how does it map to RTL? Basically, you want to have a C map to Verilog code. Okay, so a standard and straightforward translation will look like this. First, the function, okay, C++ function map to Verilog modules. Okay, it's quite obvious. And then you have an argument. Okay, the argument will map to the module's port. Okay, map to input-output port. Okay. And remember here, in C language, you don't specify the input-output, right? Yeah. So how does recognize this argument is input port or output port? Depends on its left-hand it's either on the equation left-hand side or in the right-hand side. Okay, for right-hand side, there will be input. On the left-hand side will be output. Oh. Okay, so if I use in both right-hand side and left-hand side, then we'll create two ports. One is the input port and one is the output port. Okay. They don't use Verilog. We know Verilog support in-out, but in-out really not a good practice in the design. So it will essentially two port, one is for input, one is for output. Yeah, and also type. Okay, so one of the reasons that the HLS supports C and C++ because they are strong type language. That's very important in doing the hardware design. Yeah. So in the C language, that all the variable has a defined type. Okay. And this type will affect the area and performance. Yeah, it's very important that you specify the type carefully. In the body of the C code, there are several syntax like loop. So loop is the main area that HLS optimization is performed on. That will impact the area and performance. Okay, and then the HLS optimization based on the user specified directive pragma. Yeah, and you have a control logic. Yeah, and then array. Array is very important. We use array for temporary buffer or use for the interface between modules. So the array actually often is a performance bottleneck because the array is instantial is a memory. A memory has a limited access port, one port or two port. In FPGA, there's a two port memory maximum. Yeah. And there's a expression, an operator. Operators mapping to the function units. An expression, then this part will become the data path synthesis. Okay. So we will introduce each of them briefly. First, the function hierarchy. Okay, the top level function become top level RTL, and then for example, when you write the C code, you can call sub function. The sub function becomes a sub blocks in the design. For example, so this is the Verilog code corresponding to the C code here. So you have a top module. And inside you have a function A, and function B calls function C. So you will have exactly module hierarchy as your C code, function code hierarchy. Yeah, and you can use inline to dissolve the hierarchy. And in HLS, if the code size is small, the HLS will automatically inline this module. Okay, so if you don't want the function inline, then you have to use a pragma to prohibit the inline. And for certain cases, you really want to keep the original function hierarchy. So you especially for data flow optimization. Okay, so this is a function, and we need to, in particular for top function, we will distinguish two types of top function. One is a top function that will communicate with host. So you have two types of function. One is the function communicate with host. Okay. Another is a function that's is the inside that's a part of the system. Okay, let me explain more. Okay, let's say you have a system. Okay, the system may have a multiple kernel function. It just you may have a kernel function here. Okay, you have another kernel function here. Okay, and some of the kernel function may communicate with the host. And some of the kernel functions simply interface with another kernel function, for example, using the string. Okay, and inside the kernel, so if that's the kernel, you have also have a multiple function. Okay, and then you interface with them. Okay, so the interface is a little bit different between these two. Okay, for if there's a kernel function, that means when you do the HLS synthesis, you specify this part as a top function. Okay, so you have an argument, and the argument you will specify the interface type for them. Okay, and for this communicate with host, you use some of the interface argument you will use a xi light. And for this kernel function, you really don't have anything communicate with host, so you don't have a xi light communicate with host. However, the interface between kernel and kernel, you have a few types. One is the XIS string. Basically, you use a string interface between them. Okay, the most, I think that's the most efficient way to interface kernel and kernel function. So you could provide an IP, which is a kernel function that you provide a string interface for people to, you use the kernel function using the XIS or XI master. Okay, so if a XI master, that means when you interface with another kernel function, you have to go through the memory. Okay. So if you provide an IP library, and that IP library, particularly like OpenCV, the OpenCV, you look at its library function, all the input and output image file, they use the XIM interface, memory interface. So that means for the OpenCV, if you have a sequence of OpenCV kernel function, that when you communicate with them, they use a memory. So they put the image here, and then you read the memory. You use this way to communicate these two functions. Yeah. Or you can use XIS. It's much more efficient, which is your streaming interface between these two. And inside the kernel function, that each function interface, then you will use the HLS built-in interface like the AP valid, AP acknowledge to transfer data. Yeah, that I will introduce in later lectures. Yeah. So that those type of interface is not exposed to external interface, only among the functions. And the connection between those internal functions is handled by the HLS compilers. You don't need to use a block design to connect them. Yeah, the HLS function will automatically generate appropriate interface to interconnect the multiple functions. But for here, you will use a block design, yeah, to connect them. Okay, so that's the function hierarchy. Yeah. So let's next talk about the function argument. Yeah. The function argument mapped to the ports in the RTL block. Yeah. And so for this example, we see they have a B, C input and output return. Okay, so you will generate the data port A, B, C. But if you look at the interface after synthesis, you will see other control signal comes in. Okay, for example, is using AP value type. So for those data to interchange with module, for example, this is a function, the output A to that's a function A, that's a function B, A, B, C. When they want to exchange the data, and the data comes in, for example, the A, like this. So how to know which cycle has the valid data? So you need to have a other control signal, for example, the AP valid. Okay, so you need to provide additional control signal to synchronize the data exchange. So it's obvious. Otherwise, you cannot assume every cycle the data is ready. So only the value is active, the data is valid data. Yeah. So that's where the port level protocol comes in. So when you sensor, you will generate the control ports. Yeah. And that control port will be used automatically by the design to synchronize the data exchange among blocks. And also, the whole function block need to communicate with host. Then you need a block level protocol. Yeah, that's on the top function to communicate with host. Yeah. And besides, the argument has a data type. And for the data type, you'd better use arbitrary precision bit. Okay, in this example, you know exactly how many bits you need in order to meet your target accuracy. For example, in argument A, you use a bit. Okay, and the resultant output only need 17 bit. So with arbitrary precision bit width, the HLS synthesis will instantiate the appropriate bit width for the operator. For example, in here, use instantiate 9-bit adder and 17-bit multiplication. So it has two implications. One is you reduce the resource. And second, because the bit width reduced, you may reduce the latency. For 32-bit multiplication, it may take 3 cycles. And for 17-bit, you may take 2 cycles to complete. Yeah, so you get both benefit, the resource and latency. So you should choose the right bit width in your design. Okay. So that's an arbitrary precision data type. This slide, that's I touched a little bit in previous lecture. So in this example, okay, so when you run the HLS synthesis, if you look at the interface, it generates report like this one. Okay, so for the input, you see the AP value, AP ACK. So that's use the port level protocol like this. Okay, and the in2 is specified as a in2 you specify as a AP FIFO. Yeah, in here there's an AP FIFO. So the AP FIFO map to this interface. Okay, so from this kernel function interface, how does communicate with the host? With the host. Okay, for that, the boundary will be the XI interface here. Okay, so remember in the lab 1, lab 2, you have a HLS compiler, and then you generate the IP. Okay, so that's the IP generator. For IP generator, insert the adapter. Okay, so the adapter comes out with those interfaces. Okay, so that's why when you call the IP, you actually see this interface. Those interfaces allow you to go one step to the block design. And then you use a block design to interconnect with them. And in the block design, you also insert some infrastructure component like a DMA controller, the fabric, okay, and related drivers, okay, and generate the overlay. And then, so with the block design, you connect to the host. If the U50, which is a PCI interface, actually the block design will interface with the PCIe IP. And this one, yeah, eventually generate the PCIe cycle. And this is the MPSoC. Then in here, just a PSP, or there's a XI interface here. Okay, so this gives you a whole picture in lab 2. Okay, from the HLS code to eventually communicate with your host program. So in your C code, especially we are doing the application acceleration, so it does a lot of operations, calculations. Yeah. So you will be given many lines of statements with operation. For example, like this one. And the first step, the HLS compiler will analyze the data dependency with various steps. So because you have a multiple statement of expression. And then it generates a data flow graph. So this is a typical data flow graph. Okay. And then for each operator, it has a built-in the timing library and resource. Then you will, based on that, partition. For example, in this one, it partition draw a pipeline register here. Okay, it becomes a two-stage. Becomes a two-stage the pipeline stage. Okay, so this part is a so-called data path. Okay, so that's where the data flow comes in and out. So this is a data path. And then for data path, you need to have a control logic. So that's a state machine. For this example, we generate two-state state machine. Okay, and then for each state, you will control the latch and other controls. Later on, I will have an example to go through the process. So for expression, basically generate the data path and the control path state machine. Okay. So that's how the expression is handled. Okay, let's touch a little bit more about the data path compiler. So that's a typical data path compiler function. Each part of this resource allocation, scheduling, binding, they have all sorts of algorithms. And since this course is not an EDA course, so I won't touch the algorithm. Okay, this course is basically for design. So you use data path compiler instead of designing this data path compiler. Okay. So I already talked about, first you have a data flow graph. And with this data flow graph, then you do the resource first you partition the pipeline. You determine based on the timing. Okay, for each operation, they have a map to each operation like a multiplication and adder. Then first step, you try to map a hardware resource. This hardware resource is a very high level. Okay, so that could be a built-in existing libraries like a multiplication or adder library. And for those library, it's annotated with timing and area. Okay, so given timing constraint, for example, cycle count, given the cycle count, okay, you may define cycle time is 7 nanoseconds or 5 nanoseconds. Given the user specified constraint and each function timing, then you will determine how many cycles for that. Okay, and then the last step is doing the scheduling. You decide which operation should be executed in which clock cycle. Okay, so that's scheduling. So for in this example, you put the multiplication adder in one cycle. Okay, another addition in next cycles. So by that, you have an initial binding. Okay, and this binding is to the library function. Okay. And then next step, you will map the actual resource. Like in Xilinx FPGA, for each FPGA, there is a block called DSP48. Or you have a pre-instantiated implementation for the S subsection. So this one is mapping to the actual FPGA resource. Okay, for this part, then you generate the RTL design. Okay, so in the RTL design, actually the binding, I'm not sure, probably this one is the implementation stage. Okay, so this part is in the RTL. Okay, so that's probably the RTL design. And then in actual physical implementation, you map to the actual FPGA resource. Okay, so this is the process for doing the data path compilation. Yeah, you first resource allocation, and you do the allocate the schedule, put the resource in each cycles, and then you do the actual physical binding to the actual hardware resource. Yeah. And for each step, HLS compile some, provide some pragma. For example, in here, you can limit how many adder or resource operation you can use. Okay, and for the physical binding, you can specify what kind of operation, like a latency, or what type of implementation you can use. Yeah. So that's the pragma. For this tool, you need to know the FPGA architecture more. Otherwise, if you don't know, you have a block run or the DSP. Yeah, then you don't know how to use those pragma. Yeah, in order to really do really optimize FPGA design, you do need to know FPGA architecture, and particular that FPGA device you're going to use. Yeah. Okay, array is a very important part. Okay, typically, if you declare an array, it will be implemented by a memory block. For example, like this code. Okay, and you declare an array. Okay, then this is the array, and it will be allocated with a RAM. Okay, and the RAM needs an interface. The HLS compiler will generate all the control, the interface control signals for you. Okay, so array mostly implemented by memory block. And the memory access is the performance bottleneck. It's very critical. So in the HLS design, as in last lecture we were talking about, is actually the data management, data flow management process. And the memory is a very critical part because the memory has a very limited port. In FPGA, you can have only 2-port block RAM. Yeah. In actual processor design, they can have many multi-port. For example, in modern processor, you may have a 16-port memory. Yeah, for like a register file or architectural register. Since there are many function unit will access the architectural register at the same time. Okay, in order not to make the architectural register bottleneck, so there be many ports for the architectural register. But for FPGA, the memory architecture is fixed, so maximum is a 2-port block RAM. Yeah. For example, like in this code, this operation. To do this operation, you need to get 3 memory access to do this operation. So you can imagine when I do the schedule, then you first spend 3 cycles read the memory because that's a single port. If you are using single port memory, then you spend 3 cycles to get 3 elements from the array, and then 2 other, and then write the result. Okay, so it takes like 5 cycles to complete this operation. And if you have a 2-port RAM, then you can schedule this way. Then you take 3 cycles, this 5 cycle. So you can read 2 elements at a time. Yeah, and then when you read these 2, you can perform an adder, and the second read output can perform the next. Yeah, you can. Yeah, you take 3 cycles. Yeah. So since the memory, the array is often the bottleneck, so HLS provides some memory array manipulation method for you, like you can use a reshape and partition. Yeah. So here, it's a very simple example. You can partition your memory. For example, there's an array. Then you can do the partition. Partition basically, you split an array into a multiple array. So basically, you increase the bandwidth, the number of ports. You increase the number of ports. Okay. However, partition really wastes the memory block because in FPGA, original you just need 1 memory block, and right now you need 2 memory blocks. Yeah. So the HLS provide another program called reshape. Then you can combine the memory array into a wider component. For example, first, so reshape basically first you do the partition. and then you merge these two memory into one memory, but with a wider bus, so that you can have you can access two elements at the same time. Yeah, but still using one memory array. Yeah, so that's a partition and reshape. So there are some for I will introduce in later lectures. Okay, the control flow loop. It's the focus for the parallelism. Yeah, so the loop is the main area for parallelism in algorithm. So the loop can be pipeline, enroll, merge, or flatten. Yeah, and for these things, you can use a Pragma to have the HLS compiler do it automatically for you. Okay, let's say a brief talk about the pipeline. Okay, so that's a pseudocode that basically there are two operations inside the loop. Okay, without doing the pipeline, then for one iteration you recompute and write. So after one iteration finished, then you perform next iteration. So in this example, the throughput, so every 3 cycles, you can complete one iteration. Yeah. So complete the whole loop, then you need 12 cycles. So if you apply the pipeline, then the next iteration can start before the previous iteration completes. Yeah. So in this example, so after the read, then you can start the read for next iteration. So in here, you will see when you're doing the pipeline, the 3 operations actually running concurrently. Okay, read, compute, and write all happen at the same time. So you have to duplicate the resource in order to do the pipeline. Yeah. But if you do the pipeline, you will see the throughput will be 1. So that means every 1 cycle, you can have a 1 iteration output generated. Yeah. So you reduce the latency from 16 to 6 cycle here. So that's the benefit of a pipeline. And for iteration, for the for loop, normally by default, the loop is a row. Okay. So that means they don't share for each. For example, like here, you're doing the addition for each element of a array. Okay. So since it's a row that you use the same operation in each iteration. Okay, so that's the row type. Okay, so the resource is repeatedly used in loop iteration. Yeah, so for this row loop, then you efficient in resource, but you take a longer latency. Yeah, another way you can enroll to provide more parallelism. Okay, so you use a Pragma enroll. Okay, for example, like the previous code. Okay. And then you can have a full adder instantiate, and everything, the full addition done in the same cycle. Okay, so when you enroll, you duplicate multiple operator, but what's really difficult is you must provide full element of a data as in one cycle. Okay, so when you enroll, not just the operator, often the memory bandwidth is the bottleneck. So in here, you need to provide full port of a memory so that you can access full element at the same time. Okay, so for enroll, you have two bottleneck. One is the operator, one is the memory. Yeah, often memory is most critical. Okay. So the enroll. Another type of parallelism is called data flow. Okay, that's will be our main focus in our HLS design. Yeah, because remember that FPGA, one of the key advantage of FPGA is the data flow architecture. Okay, so we should extensively use the data flow mechanism. So here, give you a rough idea how the data flow works. Yeah, let's say that I have a function that has two filter, sepia filter and followed by sober filter. Okay, and then you have an image first processed by the sepia filter. So when an image complete, then you have followed by next sober filters. So you can do the pipeline. Okay, you can do the pipeline. However, the sober filter can only start running after the whole image been processed by sepia filters. Okay, so sepia filter has to finish all the write to the intermediate pixel, and then sober filter. So it takes that. But actually, if you have a data flow, the sober filter can start right away when the data is ready. So when the sepia filter produce one output, and the sober filter can start running. So if this tool has the same throughput, then you can reduce the latency, also reduce the internal FIFO. For this one, you have to allocate big memory to save the whole image. Okay, but with data flow, you simply use a FIFO. Okay, and the depth of FIFO really depend on the latency and throughput of the cascading functions. If these two back-to-back function has the same latency and also same throughput, the FIFO may be just one simple register, right? Well, once they produce and then immediately takes away. The next cycle you produce, next one. Yeah, so you don't need a big memory to save the whole image. And also, you save the latency, right? Yeah. Okay. But again, that in order to do the data flow design, you have to make sure the data generated by the previous stage will be used by next stage. Okay, so you could not have a random access. You can now write to the image random address and expect that to be data flow to next, unless they all access the data in the same sequence. Yeah, so it's pretty obvious, right? Okay, so that's the data flow. So in here, I would like to mention that it does exist the case that this two back-to-back data flow function access in different sequence. Okay, not the perfect data flow. Then it will introduce the intermediate data structure to buffer or manipulate in a way that you can still do the data flow. But this tool does not access in exactly the sequence. Yeah, and so that's another key design techniques that will be introduced in later. Yeah, in many of the computer vision or image processing, or especially doing the convolution. Yeah, convolution that have that kind of characteristics. But you still can work around that as long as you introduce certain buffer in between. Yeah, but not a buffer to save the whole image. You just a small amount of buffer that will be sufficient. It does not change. Okay. Okay. Next, I will take another like two example to illustrate the HLS process. First, let's talk about the expression data path. Okay, and in here, that's actually when you do the Verilog code design, you probably follow the exact design methodology here I introduced. But HLS is simply make this as an automated process. Yeah. So what you're learning here is also good when you do the Verilog design. Let's say that you have a sequence of statements like that. Okay. First step, you form a data flow graph. Okay, and it shows all the dependency here. Okay, like A plus B. Okay, and the V output will add with C. Okay, so there's a data flow, data dependency like that. And for this one, you have a critical path here. Okay, because there's a multiplication, take a longer latency. So that's a critical path. Okay, and then depend on how many resources you have. So this is a resource allocation. Okay, when you do the resource allocation in here, you specify that I have only 1 meg to use. Okay, then you rearrange the data flow, and then you find out that you need 6 cycles. Because you have only 1 operator available. Yeah. And then if the user specifies, oh, okay, I can use a 1 adder and 1 multiplier. I provide 2 operator resource. In this case, the data flow graph can form like this. It then take a full cycle, complete operation. So you can have a adder and multiplication running at the same time. Okay, so if that's the result you want, the next step then how you generate the design for that. Okay, the process is exactly when you do the Verilog design, you do this way. Okay, yeah. Okay, so right now you have a data flow graph, and then you decide you have a full cycle. So you design a state machine. You design a state machine. The state machine will be easy, idle. State 1, state 2, state 3, state 4. So you have, okay, 5 states. Okay, multi-cycle, you have states. State, once you decide how many states you have, then you do the state encoding. Okay, then basically you say state 1, idle state will be 0, 0, and state 1 will be like that. You do the state encoding. And state encoding also has the techniques. If you don't assign the state encoding good enough, then you will create certain problem. One, you may waste certain logic gates. And second, may introduce glitch. Okay, that means for one state to next state, if you have a multi-bit transition, and due to the delay of a different bit, then you will generate glitch. Okay, and sometimes glitch does not matter because it's synchronous design, but glitch does create. If you want to use a combination of a state to control something, and that control signal create a glitch, it's not good. Yeah, it's all depend on how you're gonna to use the state variables. Yeah, but that's a tedious. It's supposed to teach you in the logic design course. Yeah. Okay, so you design the state machine. Okay, and then in here, how do you design your data path? Okay, first you know you have a 2 operator. Okay, and then you have how many states? Because for each pipeline, look at here. When you draw the line, you know there are how many states will be across the pipeline stage 3, right? The maximum there's a 3 course point, and here there's a 2 and there's 3. Okay, so you will have a 3-state register. Okay, so you have a 3-state register and 2 operator. And for each operator, like for addition, you have 2 arguments, right? You have 2 input, and for each input could from 3 states. So you introduce a max here. And then for each state variable, you have a different input, so you have a max in front. Okay, so basically that's the data path. So right now the problem is, how do you control the register, the state, and the max? So that's the type of a control signal will be created from your design. So the way to control that is draw the truth table here. You draw a truth table here. In here, the truth table, you list all the states and operator. And for each operator, you have a control signal. Okay, particular, that's the max. All the max, select the max. And the register enable. Okay, then you look at for each state, what this control signal will be looks like. For example, at the first state, you want to have an adder, a multiplication. For adder, you choose A input and B. Okay, for this adder, you have 2 max, 2 operand inputs, and you choose R1 and R2. R2 is B. And for the multiplication is R2 and R3. Okay, so that's the truth table. Then from the truth table, you generate each control signal. For example, enable 1, this control signal, enable this register latch. How do you generate the enable 1? Enable 1 here. So you look at truth table, you see there will be active 1 in 3 states, as state 1, state 3, and state 4. Okay, so the equation for enable 1 will be S1 or S2 or S3. Okay. So by this time, you probably finish your design. Yeah. And that's the data path, exactly like this. And the control signal will be based on this truth table. And then you complete this design. Yeah, not very difficult. Yeah. Okay, so that's for the expression data path. Let's look at another example for control flow. Particular, I'm talking about the this for loop here. Okay. And for the for loop, again, yeah, first step, you draw the control flow graph or the data flow graph. In here, there's a control flow graph. Okay, so you have a state initialize accumulator and the index I, and then next step. Yeah, so this is actually from compiler, right? Yeah, it generates this sequence of states. Yeah. So if an index less than 128, then you load the A array, and then you add, and then you increment the index. Yeah. If equal or greater than 128, then you finish. Okay. So from this state diagram, you identify your state variable and operand. In here, what's the state variable you have? You have the I. You have the accumulator, and then you also need to save the load the A array, and then you need to generate the address to access the memory array. So those are the state variable you need. And what's the operation you need? First, you have an adder for the index, loop index. One, you have an adder to generate the address. Okay, you have a comparator to compare the index, and you have an adder to accumulate this array. Okay, again, so you define the state variable and the operation. So the rest will follow the previous expression state machine. Okay, so then you draw the state variable. They come from all different resources. Okay. Okay, from this part, there will be the same as previous. You draw the truth table and then generate the control signal. Yeah, and that's a control signal. And then that's the data path. Yeah. And for this part, one step further, since that's a function, it's a function that you have to generate additional control signal. For example, down. Okay, that's a status you need to tell the host program. And then you also need to generate the control signal for memory rewrite control and the memory address and the output of accumulator result. That's an interface signal comes in. Okay, the reason I introduced this is you need to be able to read the interface, the scheduling, and resource. Okay, so I will advise you when you do the HLS synthesis, do carefully study those reports. Okay, and try to understand what's happening here. Since you have a little bit background about how the C code translate into the design. So maybe you have a capability to read these things. Okay, so let's take this example. If you run through the HLS, then you will know, okay, this is a block level design used to communicate with the host program. Then you have a memory array, so you have an output for the memory access, and you have the result that's a return, because the return here. Okay, and then you need to study the scheduling, and in scheduling you find out here it takes 2 cycles. Okay, the first cycle. Okay, let's try to read here. So you have a index variable, and this index variable will be used for comparator. Okay, this goes to comparator, and you have to use that for incrementer, right? And then you also use the index to generate the low address, memory address. Okay, the incremental, the adder comes back to load into the index register. And then you spend 1 cycle to read the data, memory data, and the data comes in to the adder. Okay, spends 2 cycles. That's what does in the first cycle, and that's the second cycle. Okay. And then you can try to understand what's the resource being used. In here, we know there are 2 adders. One is the adder for index. One is the adder for the accumulator of the memory array. And you have a comparator. So for the expression, you use 3 operations here, 2 adder and 1 comparator. Yeah. And you have a multiplexer. Yeah. And that you have the index, because you need to initialize to 0 and find the incremental. And then you have state machine accumulator. Yeah. Okay. So that's the output. But one thing here, in the original, you have this part, right? To generate the address, memory address. You remember we should have a 2 adder here, a 3 adder. Looks like the memory address here, this part is disappear, right? From the resource. Okay, you don't have this adder. And this adder actually exactly is the index, but the difference is there's no memory offset here. Okay, the memory array. Okay, first you need to load the initial memory array address, and then you increment them and generate the memory access address, right? Yeah, but if you study the HLS report, it doesn't include this part. Okay, if refresh your memory, this part is actually not in the HLS. Remember, you have a HLS compiler module, and you have a adapter, right? You have an adapter to generate XI master. Okay, and so this base address is actually in the adapter. So you simply give the offset and add the memory A array A base address here and generate the master address. Okay, so this part is in the adapter, not in the HLS code. So in HLS, it doesn't need this adder. Yeah, this adder is actually in the adapter. Okay. So yeah, this conclude the two. Okay. So the time is almost up. Yeah, and there's another question for this example. Probably take home. You can try to exercise this. So given the code below, this code, assuming the following resource: first, A and B array is in the same memory block. In the same memory block, and this memory block is a single pole memory. And the C array actually has a separate memory block. And this multiplication is a 2-cycle latency. Okay, so when you want to do the pipeline, what is the II? I means when how many cycles it takes for the next iteration start. Okay, remember when we are doing the resource, doing the pipeline, that these things will overlap. Okay, the iteration will overlap. Then you should draw the timeline and see based on this resource constraint. Then you try to calculate when the next iteration can start. Yeah, which is the II. So you can take home. Yeah, maybe you can answer in the forum. Yeah, anyone can answer that in the discussion forum. Yeah. Okay, so let's conclude today's lecture. Any questions?